I'm going to introduce the concept of normal distribution to you. Okay? And after today, I'm certain you're going to actually like pick it up if you hear it. You may have heard it before, but you're like not sure what that means, right? When you think of normal distribution, I want you to think of a bell curve. Okay? And COVID, they talked about flattening the curve all the time. It actually goes straight back to this, okay? It is a probability distribution. This is important. It's symmetric. It's symmetric about the mean. It's showing data near the mean are more frequent. So data that is closer to the mean are usually more frequent in occurrence than data that are far from the mean. In a graph, the normal distribution will appear as a bell curve. And I'm going to use a different color for this part. This is important, this concept right here. The mean indicates the location of the curve along the x-axis. That's one color. And then another color for the one that follows right after. The standard deviation indicates the scale of the curve along the x-axis. It's almost like, I will make a note here. This will make more sense to you later. Determines the width of the bars. And I'm going to put this in quotation marks because it's kind of like for us that will make sense. I don't know if any other teacher would necessarily use that, but the standard deviation tells you how wide the bars are going to be that we're going to graph. Okay? A large standard deviation will stretch the curve, flattens the curve. So I don't think this is new. A large standard deviation will flatten the curve. A small standard deviation will squeeze the curve, will make it steeper. Okay? Symmetry indicates that half of the values are below the mean and half of them are above the mean. It's also important. So all of these concepts are important, but in particular the orange and the green, those are important when it comes to graphing. Examples of data that follows normal distribution. It turns out that humans, a lot of attributes like height, weight, the migration of birds, right? Like when the geese start coming, let me just give you a little illustration. At first you don't get that many, right? But then there's like, all of a sudden there's more and more and more, and then there's that peak when most of them are arriving, and some of them come way later yet. Okay? So you can see that bell curve. Baby birds hatching in the spring, right? You've got some very early birds that hatch really early, and then more and more and more, and then you get to this peak, and some are born later, some hatch later, and that happens too, but you have like your concentration is around the mean, okay? Amount of traffic at a certain time of the day, right? Rush hour traffic, it's slowly, right? And it picks up towards a certain peak time, and then it slows down again. COVID admissions to the hospital, right? What the hospitals did not want, they did not want a curve like this. Because that means that a lot of people would just show up all at the same time. And that would just overwhelm. They wanted the curve to look like this. Okay? This flattens the curve. So that way, like, you have all your patients kind of spread out. You don't have them all showing up at the same time. We have no beds now. We have no doctors. We're in big trouble, right? So the system wanted people to get sick, like distribute that sickness, right? Like so that we don't all get sick at the same time, the cycle of getting sick. And so here's the graph with information that I'm about to give you, okay? So I'm going to fill this graph up quite a bit. mu, right? This one right here, mu is like our average. This is where you can write down the mean. Mean or average. Write that down. I'm going to highlight that. Okay? If you think about it, that cuts our bell curve in half. Okay? Cuts our bell curve in half. 50% of our values are going to be below it. 50% are going to be above it. Okay? So I will write that down on the side here, that this is the mean or the average. And you're like, Mr. Rickson, didn't you say that average is x with a bar? Didn't you say that? Yes, that's also true. So welcome to a lot of things are true at the same time. Okay, but when we talk about the bell curve, we use the letter mu. Go figure. Okay. Okay. One thing that we've observed in a normally distributed data set is that, I have to be careful here. Let's imagine for a second that the standard deviation of this set is 5%. Like someone's score, let's say the average score for this class is 70%. And the standard deviation is 5%. Follow me here. If this is 70, then this would be 65. This would be 60. This would be 55. Right? Let's go the other way. If this is 70 and the standard deviation is 5, this would be 75, 80, 85. All right? I'm not going to put numbers down because the average and the standard deviation will change all the time. It depends on what we're talking about. Like let's say we talk weight. If the average weight is of, let's say a cow is 1,000 pounds with a standard deviation of 20 pounds, this is 1,000. This would be 980, 960, 940, right? So think about it that way. And you might wonder, why is it only 3 standard deviations to the right and 3 standard deviations to the left? Like, why don't we keep going? And the reality is because past the 3 standard deviations to either end of the mean, it starts to be almost nothing is found in there. So we're just focusing on 3 to the right, 3 to the left. Okay? So what we found is that if you take the mean and you go 1 standard deviation below and 1 standard deviation above, we find in general 68% of our data points are going to be found there. So write that down, the 68%. Okay, so this is within 1 standard deviation of the mean. The mean is the main character. If we go 2 standard deviations to either side, so this is the mean and we go 2 standard deviations to either side, it's known that 95% of our values will fall within that. So 68, 95. And this one, if you go 3 standard deviations to either side of your mean, it's said that it's 99.7% of data values are in there. So, because of symmetry, if it's 68 here, then it stands to reason that it'll be 34 and 34 on either side of the mean. So this bar has 34% of values, this bar has 34% of values. If you go even further, this stretch right here is 13.5, represents 13.5% of the values are found in here. And it's 13.5% over here. Wait a minute, where did you get those numbers from? If you were to add these 4 bars, it should add up to 95%. Okay, so that's what I'm trying to tell you here. In here, in this little, so the sliver is getting, like that area is getting smaller and smaller. In here, Make sure you can see this, okay? It's 2.35%. 2.35%. I'm not going to go percent there. Can you see that? 2.35. And here it's 2.35 as well. Let me zoom in a little bit here for you folks back there. So if you add up, watch this. There's 3 bars here and another 3 bars there. If you added up these 6 bars, you would end up with 99.7% of values landing in there. Okay? Then this sliver, do you see that sliver? I had to work really hard to let you know that this is not touching here. There's actually something underneath that little flap. And that's 0.15%. There's not a whole lot found in there. But when it comes to income, let's talk about income. Elon Musk would probably be here. Bezos, right, the Amazon guy, he'd probably be under this little flap there in terms of income, because they make so much more than everybody else, right? So there aren't that many people making that much money, okay? But if you found the average income for everybody on the planet, most of us would fall, right? So 95% would fall within 2 standard deviations and so forth. Is there anything else I need to mention right now? By the way, can you write down along the x-axis, this could be height, weight, income, volume, time, etc. Okay? So the x-axis will depend on what are we talking about. Hours of sleep, hours of work, okay, screen time, you name it. That's what this could be. And frequency is usually, it's going to be number of values that we've entered. But this y-axis, I'm not going to graph in general. We're just going to graph the bell curve, okay? I'm just showing you that technically there is one. Okay. Is there anything else? One more thing. There's something called the z-scores. Z-scores. For now, just write them down for me. So the mean or standard deviation under that one, you have a z-score of 0. Under this first one right here, you have a z-score of 1. Here you have a z-score of 2. Here you have a z-score of 3. If you go to the left, you have a z-score of -1 right here, a z-score of -2, and a z-score of -3. For now, the z-scores, I will explain that in a little bit. Next, the percentage in each section represents, highlight this please, the percentage in each section is the likelihood or probability of data falling within that interval. Say what, Mr. Dirksen, say what? Let's go back to our average. Remember when you had the average score of 70 and the standard deviation of 5? Average is 70, so this would be 65, right? So the chances that a student in this class had a mark between 65 and 70 is 34%. Like if data is normally distributed, we would say there's a 34% chance that a student falls within this, a 65 and a 70, okay? So these are all probabilities. These are all likelihoods that that's going to happen, okay? So the government, let's say they talk about income, and they say, hey, the income of families is normally distributed, then they can say, oh, if our average income is 80,000 and our standard deviation is 10,000, this would be 70,000, this would be 90,000. Okay, so they kind of have an idea. 68% of families make between $70,000 and $90,000. Okay, so these are probabilities. I know I'm overwhelming you a little bit with information. It might make more sense later on. Another one here, normal distribution follows the 68, 95, 99.7 rule. It's called the empirical rule. So we have to observe the 68, 95, 99.7 to say that something is normally distributed. A larger standard deviation results in a flatter curve. Smaller standard deviation it will result in a steeper curve. The total area or probability under the curve is always 1 or 100%. Like you cannot have more than 100% of data points. It's just not possible. So it's either 1 if you do it as a decimal or 100% if it's a percentage. Here, I added this brand new for you guys, okay? Because students had problems. If it says at most 50 kilograms, at most 50 kilograms means less than or equal to 50 kilograms. Okay? I will, you can also say no more than 50 kilograms. At least 30 milliliters means 30 milliliters or more. So I will highlight this part and I will highlight that part so you are familiar with that terminology. It's like an inequality terminology. All right. Let's apply this. I will ask you to write these formulas down for now, but we're not going to use them not until tomorrow. This is on page 25. Calculating z-scores by hand. When you're given the mean and the standard deviation, you can use the following formulas. So to calculate the z-score, you go value minus x bar, that's the mean, divided by standard deviation. To calculate the value associated with a certain z-score, I use the same formula, I just rewrite it. It'll be z times standard deviation plus the mean. And I won't tell you what all the individual entries mean, because you already know at this point. And just a note, z-score is given, right? You can't use that one unless you have the z-score. I will ask you to write down nice and big here, z-score one more time. What is the z-score? The z-score tells us how many standard deviations above or below the mean the value is located. A negative z-score tells you that the value is going to be below the mean. A positive z-score means that you're above the mean. I'll give you a quick example here. A mark of 85% with a z-score of 1.8 tells us that 85% is 1.8 standard deviations above the mean. Sorry, that's very small. I'm going to zoom into that. All right. Let's try this here. So let's do the first question here. So I gave you a bell curve, so we just have to fill that in. The height of males in Canada is found to be normally distributed. Okay, very important, because that tells us a whole bunch of things that we already know from the previous page. Not everything in life is normally distributed, okay guys, just so you know. We'll check for that later on. The mean height, the mean is 177, and the standard deviation is 2.5 centimeters. Graph the normal curve indicating the percentages within plus or minus 3 standard deviations. Include the z-scores as well. So we'll do that. Since the average is 177, we put this down right here, 177. And we're going to use, from there, we're going to go to the left. As you go to the left, we subtract a standard deviation. So we're going to go minus 2.5 centimeters. And then we're going to keep going, minus 2.5. And we're going to keep going, minus 2.5. Let me show you what this is really saying. Take the mean and then go minus 1 standard deviation. Then you're going to get this value. This one is saying take the mean and subtract 2 standard deviations to get this one. Take away 3 standard deviations to get this one. So you can either just take your calculator and I'm going to suggest use your calculator for these ones because sometimes you're off by a little bit. So this will be 174.5. Keep subtracting a standard deviation, right? That's 172. Keep subtracting. That's 169.5. And then you do the exact opposite going to the right. Okay? We're going to go 177 plus 2.5. That's 179.5. So I'm going to go to 177. I'm going to go arrow to that value. I'm just going to say that I'm adding a standard deviation, and I'm going to keep going 2 more times. So keep adding 2.5 to it. Sorry, you can see that, right? And I forgot to label. This would be the height. X-axis represents the height in centimeters. So if you have that labeled, you do not need to include units along the x-axis, just have numbers there. I'm going to do the z-scores right away as well. So what I tend to do is, I'm just going to make a line here to clean it up a little bit and just say z-scores. The mean has a z-score of 0. 179.5 centimeters has a z-score of 1. Positive, and then it's 2, and then it's 3. You go minus 1, minus 2, minus 3. So the values that you can see here, each value has a z-score that goes with it. So if I say, oh, a z-score of -3, you're like, oh, you mean a height of 169.5 centimeters. Is that what you mean? Yeah. So later on, we're going to see how we can use the z-scores instead of the actual score to standardize things. Okay. And remember, the z-scores can be anywhere in between. Like there could be a value anywhere in between here. Right now, we're only seeing these ones here to give us some reference. And fill in the percentages. It's 34, 34. You know what I do? What I used to do to memorize? I would memorize 1/2 of the bell curve, and then you just duplicate it on the other half. So I knew that this is 0.115%. This is 2.35%. This is 13.5%. And that's 34. Right? So you know from left to the middle, and then you just keep doing that going to the other side. If you want to put the 2.35 outside, just have an arrow to it. That's fine as well. So we've got, I'm mostly interested with you including within each bar, guys, within each interval. If you want to go 68, 95, 99.7%, that is fine. I don't really require this on a diagram because if you know these percentages, you're good to go. You know what you're supposed to do, okay? Now what about this bar here, Mr. Dirksen? Do I care about it? Not really. Like soon I'm going to get rid of it because this represents percentages. So when we do stats and we look at the bell curve, we don't no longer look at the frequency here. Okay. Okay, so now we can answer a bunch of questions using this bell curve. What percentage of males are between 172 and 179.5? So 172 is right here. 179.5 is right there. You're with me, right? Let me use 2 pencils because my fingers are too big. They cover everything. 172 is right there, and 179.5 is right there. Okay? So this is like your start line. This is your stop line. So we're going to add up all the percentages that are found between these two heights. Okay, guys? So I'm going to show my work here. Okay, if you add that up, you get 81.5% of males are expected to be between these two heights that you were given. Okay? What percentage of males are expected to be at least 182 centimeters tall? There's that word that throws students off, at least 182. So I translated it for you. Are taller than 182. At least means 182 or more. Okay? So you go to 182, you found it. So it's everything from here all the way to the right. So it's basically just adding up these two percentages. Okay? So we're going to go 2.35 plus 0.15, and that's 2.5%. Let me see if you're awake. If I asked you how many males are shorter than 182 centimeters, what would you do at this point? Shorter than 182. You would add up everything to the left, correct? But there's a faster way. What's the whole bell curve? It's 100%, right? Including these little tails here, it's 100%. So couldn't you just go 100% minus 2.5? Then you get all the ones that are shorter than, right? So you're going to start finding shortcuts. Just be careful not to make too many shortcuts and then make a mistake. But that is a possibility. Okay? What percentage of males are shorter than 169.5? Or in math is plus, by the way. If you're taking grade 12 applied next year, it's going to come in very handy. Or taller than this. So I'm just going to make this little bell curve here real quick. Just a sketch, right? 169.5 is right here. So we want, if this is 169.5, it's right here. So we want everything, all the folks that are shorter or taller than 179.5. Where is 179.5? It's right there, correct? So it's somewhere here. So we want to add this. We want to figure out how many are shorter than 169.5 and how many are taller than 179.5. That's what we are interested in, figuring out these two combined. So let's figure out this and then add it up. Okay, so shorter than 169.5 centimeters. What are we at there? We don't need to do a whole lot of math, right? Shorter is 0.15. It's right here. Taller than 179.5. Let's figure that out. 179.5 is right here. So I go 13.5, 2.35, and 0.15. Is that 16? Yeah, it's 16%. 16%. Okay? So shorter is this, taller is that. We need to combine them. So it's 16.15% are shorter than 169.5 or taller than 179.5. I'm going to use my pen here. I'm just going to show you one more time. This is 0.15%, and this ended up being 16%. And I combined them, right? I combined them to give me this. So the wording is going to be key here for you to pick it up, okay? Keep going. If I run out of time, guys, your only homework is going to be the bell curve with all the percentages on your study sheet with a normal distribution at the top, okay? That's it. Watch this here. So I'm going all over the place. I know that, okay? What is the range of heights for 99.7% of males? Does that number ring a bell? Bell curve? Yeah. Well, what do you remember, right? 68, and then what? 95, and then 99.7. So what is the range of heights? A range means, right, shortest to tallest. Like, what is the range that has 99.7% of males in it? So we're going to go look that up. 99.7, watch up here. 99.7 means I need to go 3 to the left, 3 to the right. And the range of heights, not percentages, it's not asking you for percentages, but we're talking 169.5 to 184.5. That is the range of heights. That would have 99.7% of males in it. So we go, can you see that? 169.5 centimeters to 184.5 centimeters. This is for 99.7%. Right? 99.7% of males would be there. Let's figure out the range for 95%. Can I say this? Let me see if you can. 95 would be what? Plus or minus 2 standard deviations, correct? 95 is 2 to the left, 2 to the right. Let's go look it up. 95, we already figured it out. So it's 2 to the left, 2 to the right. So it's from 172 to 182. That's the range of heights that would have 95% of males in it. So 172, you'll thank me next year. Right now you're not too excited, I know. So that's 95% of males would be in that range. And 68, you should start to recognize, oh, 68, that's 1 to either side, right? That's how much I'm considering here. Plus or minus 1 standard deviation. So 68 would be, I'm not gonna show you on the screen, but it's 174.5 centimeters to 179.5 centimeters. I'm going to stop there, otherwise your brains are going to explode.